Now let me explain to you about the seminar. The title of today's meeting is Development of Green Materials based on Physical Chemistry. I'm a chemist, and my research area has been the development of phase transition materials utilizing chemical synthesis. Although my work is in fundamental chemistry research, I have also found ways for applied use of our science through collaboration with people in the industry or scientists overseas. Those works are linked with GX, and GX stands for Green Transformation. And this is what we would like you to know, and what we will foster through our project. The slide shows the qualifications and capabilities I think are needed in a project officer. I have been involved in some multinational activities. International collaboration has been one of my main focuses. I proposed and realized the University of Tokyo's first PhD double degree program. It took time, but we made it. And finally, the program is starting next year and will have 2 students in the double degree program. Concrete examples of achievements are important when we talk about international research collaborations. We have published joint papers with a number of research institutions. Also, I am the director of the International Associated Laboratory of France, CNRS. In terms of industry-academia collaboration, I am currently working with 10 companies with more than 280 patent applications, which is rather rare for scientific researchers. The slide describes the type of fundamental and practical research I am involved in. As a researcher in basic science, my particular area of interest has been in design and synthesis of noble phase transition materials. These are the specific types of research. Common elements are used to develop materials, some of which are subsequently developed further into practical research. Today, I will focus on some of these materials. One important aspect in this research is awareness. When you talk to people, you become aware that your research may be useful for certain purposes. Such communication with others is extremely valuable. Therefore, awareness is a very important aspect in our project and in our laboratory. The work of chemists is to produce new materials. So far, we have developed more than 500 compounds to be used for various purposes. The slide summarizes functionalities of materials. The ones on the left are called bridged metal assemblies, which is a combination of metal ions and organic molecules leading to novel functionalities. The ones on the right are oxides. Novel oxides have been found, and they demonstrated new functionalities. I'll explain some of them. The bridged metal assemblies on the right have been made by our students who synthesized materials every day for 3 years to develop new materials. In terms of functionality, our focus has been in ferromagnetism, and our goal is to develop magnets with completely new types of properties, such as photofunctionality, potent ferroelectricity, ion conductivity, or molecular sensitivity. We can design and synthesize our own structures when we develop metal assemblies. For example, this material has optical functions. Iron ions and niobium ions are bound with cyan and form this unruly 3-dimensional network. It may not seem like it, but this is 3-dimensional. The slide shows the property of the magnet. The vertical axis of the graph shows magnetization. Horizontal axis, temperature before irradiation of light. The curve is flat, but when irradiated, the curve rises sharply, indicating that the material has now become a magnet. The temperature is as low as 20 K, but you can see the magnetic hysteresis loop in the magnetic field curve. This is a type of light-induced spin crossover magnetization. Coercivity, the property of magnets, was achieved. Other similar structures have been developed. This is an example of crystals. When you develop monocrystals, two structures appear, one for positive form, the other for a negative form. This is chirality, just like having the left hand and the right hand. When you irradiate light, what was not a magnet before becomes a magnet. The first change occurs with blue light, but when switched to red light, the property is reversed. Subsequently, with alternating light, the property goes back and forth. This means that the monocrystal structure is now a magnet with photoreversibility. What can we do with this? When a plane laser wave is applied to a monocrystal structure, the second harmonic light, which has half the wavelength, or strength rather, comes out of the structure as a vertical ray. With light irradiation, the structure becomes a magnet. And the plane of light, called the second harmonic light, turns 90 degrees, and when red light is shown, the plane turns vertical, so when irradiated, the photomagnet with chirality shows 90 degrees optical switching phenomenon of polarization plane, with output second harmonic light. The structure is called chiral photomagnet from its properties. Those of you in material science may be impressed because this is an unprecedented phenomenon. It was the first observation in the world. 90 degrees optical switching phenomena of polarization plane of output second harmonic light is considered an innovative research area in the fields of material science and magnetism. A story of the research appeared on the front page of Nature Photonics. Now I move to a very fundamental basic research. As I said before, a scientist must have an exceptionally deep level of expertise to be able to solve global issues. So I start by sharing my own basic research activities. This is on the topic of ion conductivity and battery from a perspective of ion conductivity and molecular sensitivity. Everybody must have seen a magnet, but you would not expect that humidity affects the properties of a magnet. You may think of performance change and development of rust, but not changes in material property. This material is made using cobalt chromium metal ions, bonded with cyan, and it changes color with humidity. This is a material with magnet properties, but the magnet temperature curve of the material demonstrates change in the level of magnetization between 22K and 28K, depending on the level of humidity. Now, why do we see these different colors? This can be compared to silica gel. The desiccant beads contain some red beads and blue beads. They contain cobalt ions. Cobalt ions enter here. This is a complex of 4-coordinate cobalt, which transforms into a 6-coordinate cobalt complex. Then you see cobalt pink as well as cobalt blue. The colors change according to the temperature. The blue beads and silica gel turn red with humidity, and when heated to 200 degrees Celsius, the color turns back. So with changes in humidity and temperature, the colors change along with the change in magnetic properties. This is a magnet that changes properties in response to humidity, such as water vapor. This is the only one of a kind and very rare. Here's another similar material synthesized by mixing molybdenum ions and cesium, and the color is bright blue. The bottom of the slide shows its three-dimensional network of the crystal structure, rather a unit grid of a much broader network. The complex plane impedance plot of this material shows that proton conduction is induced with a trigger. The structure has hydrogen bond network internally in which protons can transit. The result shows that this is an ion conductor or a proton conductor. Irradiation of light results in changes in proton conductivity. The level of conductivity of this material is very high, falling slightly below the proton conductivity of naphthalene. Irradiation of light changed the internal structure. Molybdenum NO inside results in switching on and off of hydrogen bonding network with changing angles which change proton conductivity. You may know that ion conductivity is used in batteries. Ion conductivity has been widely studied, but this was the first optical switching of superconductivity that was reported last year. Before radiation, it has superionic conductivity, but after radiation, ion conductivity decreases by about 2 digits and it can be reversed. The research was picked up on the cover of Nature Chemistry. So far, I have given you a brief introduction of some fundamental research. Now I will talk more about some practical research activities about epsilon iron oxide and lambda tritium pentoxide. With basic research outcomes, I became interested in novel oxides. Existing oxides are interesting, but we have focused on discovering novel oxides, and the slide shows some of the new metal oxides reported by our group. Not all the novel oxides have exhibited new functions, but the ones on the slides have some very interesting functionalities. One of them is di-iron trioxide, or Fe2O3, commonly known as ferric oxide. It is transferred from gamma to alpha layers. An alpha layer is red rust. Actually, it looks bluish, but it is red. Base layers are rather blackish and sometimes used as magnetic materials, such as magnetic fluid. Typically, the changes occur as a result of changing crystal structure from gamma to alpha, but we achieve this with nanoparticle epsilon Fe2O3, which exhibits new crystal structures that are usually not visible. This is a nano-sized effect. Between 3 to 50 nanometers, the structure is most stable. The discovery of this new crystal structure was good, but there is a huge magnetic hysteresis loop. The horizontal axis shows the field, vertical axis magnetization. The two curves show horizontal separation, and this is called magnetic hysteresis, with a value of 25 kilo-Ørsted, demonstrating the largest coercive field of all metal oxides. We also know that a part of this metal iron can be substituted, and in the case of rhodium substitution, the coercive strengths reach even a higher level of 31 kilo-Ørsted. This is how a high level of coercive field strength was achieved with simple iron oxide. By making the full use of nanotechnology with simple iron oxide, we achieved such a large coercivity. We call this ferrite, and such a discovery was the first in Japan. Material with such outstanding property also has diverse functions, and one example would be a capability to maintain magnetic property even when the size is smaller. As you know, magnets can be reduced down eventually to a single atom, but it is no longer a magnet. But if a material has a high level of coercivity, it may be maintained in smaller size. For example, we achieved coercivity in a particle as small as 8 nanometers while maintaining 5.2 kilo-Ørsted. There are 3 important numbers in properties of magnets. 3 kilo-Ørsted is the level of coercivity in ordinary magnets. Below this level, there is no more magnetic strength, so we need to break the barrier. The graph shows coercivity vertically and particle size horizontally. Compared to other ferrite magnets, epsilon iron oxide, Fe2O3, can maintain a very high level of ferromagnetism, achieving 5 kilo-Ørsted even at 7.5 nanometers in the case of rare earth magnets like neodymium iron boron. Coercivity is lost when the level falls below 27. Changes made in the crystal structure enabled the simple iron oxide capable of maintaining a high level of coercivity in a small size, and indeed, this was the discovery of the world's smallest hard ferrite. What are the possible applications? The graph shows coercive field strengths vertically and Western calendar year horizontally, representing coercive field of magnetic recording medium. There has been a growing need to increase recording density. Here are the epsilon iron oxide and rhodium substituted epsilon oxide. It is expected that these materials will contribute to satisfying the need for recording requirements in 2020s and 30s, especially in the use of magnetic tapes. The photo shows the manufactured magnetic recording tape using powder we developed. You may not have seen these magnetic tapes, but they are very important. The other photo shows the magnetic layer of the tape. The size is below 100 nanometers. The power spectrum shows a very sharp increase, demonstrating that the replay signal is very effective as a magnetic tape. The market size for magnetic tape is quite large. The slide says 600 billion yen, but it is rapidly approaching 1 trillion. Now, why are magnetic tapes important? That's because we are entering into the era of big data, and we need magnetic tapes for industry-scale records. And this is a very different from what we used to use, for example, Walkman. In order to achieve a huge volume of data, you need capacity. Records kept for pension bank accounts and life insurance from 100 years ago have already been lost, although now many people live beyond 100 years old. Losing data is no longer acceptable, and all kinds of data are needed, but cost of recordings has been very high compared to such media as flash memory and optical disc. Magnetic tapes can record data at a very high capacity per volume because tapes are rolled. The cost is low, only 1/100th of flash memory, because when not in use, it can be piled up somewhere. It is also beneficial in terms of CO2 emission because you do not need electricity when not in use, so the cost is 1/10 of hard disk drive. We need to consider SDGs while having to keep records, but now the cost of maintaining records has become prohibitively high. If you consider all the documents in our history, including Murasaki Shikibu's world first novel, or the recordings on papyrus in Egypt, and if you piled up all the records, indeed 90% of them would have been recorded in the past 2 years. That is the speed of growing need for recording. Soon we will run out of capacity, but we need to keep records, which means developing new recording methods will be very important. Magnetic tapes may be used only once a year, but the recordings may not be lost, so magnetic tapes will be a good media for records. The photo is from the Data Library Center of Google. Several years ago, the cloud system failed, and records were lost. Some Japanese companies also suffered, as well as Twitter, but after only 1 week, all the data was recovered. How was this possible? Because they have a data center in Alaska where there is a row of magnetic tape decks, like these, in a huge room to keep backup records. We found out about this backup for the first time. So now we use Google and our data is in the backup system, using tapes, and such tapes must be inexpensive. Because data should not be lost, and this is where our materials may have roles to play. Fujifilm is one of the top manufacturers of magnetic tapes, and the companies, including our epsilon iron oxide, in its list of candidates for their magnetic products. This photo is from an interview article with myself and a board director of Fujifilm. Another possible industrial use of our epsilon iron oxide would be an absorption of electromagnetic waves. One role of magnetic material is recording, but absorption is another. Automotives benefit because of absorption of electromagnetic waves for insulation with a large course of power. It is also expected to work with a very high frequency level. In the field of communication, millimeter waves have become important because of much progress in the industry due to the arrival of the IoT society. One good example would be an onboard millimeter wave radar for 76 to 81 gigahertz. WiGig is another example. We now use Wi-Fi, but in the future, higher frequency of WiGig will be needed. Wi-Fi range is 2.48 or 2.45, but WiGig will be for 60 gigahertz. Higher frequency will be needed at airports for millimeter wave scanners, for broadcasting wireless communication, or driving safety support systems. ADAS requires 140 gigahertz. Wireless communications use 1.5 gigahertz or 800 megahertz for mobile phones, but for wireless communication in between ground stations, the frequency level required is 140 gigahertz. Because they need a very rapid transmission. In such ways, magnetic waves are used for various purposes, and while Wi-Fi frequency is 2.5, WiGig is about 60 gigahertz, allowing 100 times faster transmission speed. What takes 1 hour now will be sent in seconds. So various levels of millimeter waves will be used in the future, between 30 and 300 gigahertz. So electromagnets lead the IoT society. The fifth generation of the mobile phones, 5G, is currently in use. 5G uses 3.5, 4.7, and 23 gigahertz in Japan. But in the age beyond 5G, when we will have a 6G and 7G millimeter waves, will be the key for wireless communications. So there will be a diverse use of high-frequency electromagnetic waves, but that will induce confusion of lines interference and various other issues. Also, we do not have to be exposed to unnecessary electromagnetics. Data theft could occur in an instant, and all the information may be snatched away, so for security purposes, data absorber will certainly become necessary. These are absorption products. We have found that Epsilon Fe203 is capable of absorbing 180 gigahertz. Also, by substituting metals, we can shift to different levels of frequency. Substituting with aluminum, gallium, or rhodium, we developed absorbers to cover all the wave ranges. There was a BBC program about our work in 2007. We announced that we developed absorbers up to about 150, 140 gigahertz. Then, in 2009, we announced that we exceeded 180 gigahertz. It was more than 10 years ago when we gained much attention, but IoT society was yet to arrive, and people only said it was for the future. However, it was proven that perseverance is important, and now I have become an authority in millimeter waves absorption. In 2009, it was a hot topic, and BBC News program and others reported the discovery. Tens of thousands of websites around the world mentioned our product. Then things progressed, transmitters progressed, prices fell, and all of a sudden cheap transmitters were made available. Then very soon, millimeter wave and beyond 5G waves are in use. Our absorbers are gaining much attention, so currently we are prototyping various products with companies. There will be a variety of absorber products available, especially in the world of big data and IoT for security of big data in the IT society. The photographs are from an exhibition held in Science Museum of London. This is a museum for science and technology, while the British Museum exhibits historical items. There is a special edition held at the Science Museum, and we were invited to exhibit along with Google, Facebook, Twitter, and Cambridge University. Facebook exhibited an 800-kilogram deck of magnetic tapes. Cambridge exhibited items related to encryption processing, and we demonstrated our absorbers to show physical absorption of electromagnetic millimeter waves. This is a powder form of the product. The name of the company that markets the product is on the slide. This company sells films and inks. The company sells a very thin film millimeter wave absorber with high performance. This company markets a broadband radio wave absorbing sheet. For car radars. Onboard use is quite common at around 79 gigahertz. The absorption rate is 99.8%. This is a very thin and lightweight product. The company name is on the slide. We are working with Fujifilm in order to increase recording density of magnetic tapes in the future. To enhance recording capacity, we must improve. Records are written with magnetic fields both for hard disks and magnetic tapes. When recording, there are limits as to how much you can change the flux density in order to increase recording capacity. Our materials that are capable of absorbing millimeter waves are expected to make contributions in the next generation of magnetic tapes. In combination with millimeter wave absorption capability, we designed a focused millimeter wave assisted magnetic recording. We filed for a patent which was granted, and we published a paper on demonstration work 1 year ago. Through this effort, the development of the millimeter wave-assisted magnetic recording method on magnetic tape was adopted as a national project for new technology. My last topic is on heat storage materials. We have the Heat Storage Material Lab as a part of Ohkoshi Group, and also as a part of the groups within the University of Tokyo Institute for Open Innovation. Let me explain this. This is a topic of thermal energy, or specifically, utilization of emitted heat, because reuse of wasted heat has become very important. The graph shows the temperature of emitted gas relative to the caloric content of emitted gas. In other words, how much energy emitted at which temperature level was wasted and used. Released heat above 500 degrees Celsius will be a very expensive waste. Under 200 degrees, a very large amount of gas is emitted and mostly wasted and used because it cannot be stored and simply released in air or in seawater. Of the input energy from such resources as natural gas, petroleum, and nuclear fuels, 38% is lost as unused heat. These include factories and power plants. Of the unused heat, 78% is below 200 degrees, emitted because it cannot be stored. So, we wanted to find ways to make the best use of such released heat. Because we burn fuel, use fuel, convert fuel to energy, but a lot is being wasted. Therefore, the concept of heat storage becomes very important. The simplest way to describe heat storage materials, the easiest to understand, is like bricks and concrete. There are slow cooling materials called sensible heat storage materials. Then, like water, paraffin, and polyethylene glycol, using solid liquid phase transition, there are latent heat storage materials. Then there are things like pocket warmers that burn iron powder, which becomes iron oxide, but that's a one-time transition. The heat storage material I'm showing now can come and go. It has reversibility. The problem with these thermal storage materials is that over time, they release their thermal energy naturally, so the heat cannot be stored if the thermal energy could be stored long-term and retrieved at the desired time as renewable energy. It could be effectively used. There were great expectations, but this wasn't possible with heat storage materials. This is called the time gap problem. It's like a blue rose, a synonym for something that can't be done. Now, we wanted to solve this problem, and I'll explain how. Now, here is another material, titanium oxide. Titanium oxide is one of the most familiar metal oxides, and it's used as a white pigment. The white color of the walls is the color of titanium oxide. It's a pigment, and also used as a photocatalyst. On the other hand, there are other types of titanium oxide with different valences, such as titanium tetravalent. Chemically, it has no 3d electrons, d equals 0, or with only one d electron, made from titanium trivalent. That's Ti2O3. It's a black pigment, like this, like eyeshadow. It's pitch black. It's also used as a heat-absorbing material, and using only titanium tetravalent and titanium trivalent from pure white to pitch black, we can get such a variety of materials are so interesting. And with this material here, there is a metal insulator phase transition, or an electrical transition, or an antiferromagnetic transition, or a magnetic phase transition. You can also mix titanium 3+ and 4+. There are various valences starting with Ti2O3, Ti3O5, Ti4O7, and so on. You may also remember from your chemistry entrance exams, titanium 3+ multiplies by 2, titanium 4+ multiplies by 2, and 2- multiplies by 7, and we get 0. All substances must be neutral, so we get this composition. And in any case, when titanium trivalent is included, it takes on a pitch black color, and in patterns we sometimes call this black titanium oxide. So there's white titanium oxide and black titanium oxide. So what did we do with this? White titanium oxide nanoparticles have been studied considerably for various applications, including photocatalysts. But what we did was this part, which hasn't been studied pretty much at all, and we made nanoparticles of this part. Basically, this is a material that undergoes phase transitions, so it has phase stability. And we thought that by making nanoparticles of it, we could produce physical properties that cannot be produced in bulk or single crystals. As a result, I'll skip the synthesis method. We discovered a new type of titanium oxide in 2010, as you can see in the upper right. We named it lambda trititanium pentoxide and announced it as a material with a new form of Ti3O5 structure. Now this material is rather complicated to make. We managed to trap nanoparticles in glass. You get this crystalline structure. And the glass can be chemically etched to remove nanoparticles, but we wanted to make large amounts of nanoparticles, so we thought of targeting small particles and avoiding growth into crystals. That's what we thought of, and the result was we were able to get large amounts. At first glance, it looks like a huge coral reef. This is 2 microns. The previous page was 20 nanometers. So if you look at the one on this side, it's 2 micrometers, which is 2,000 nanometers, which is 100 times the size. That's what it looks like. But if you look inside, this is a TEM photograph. If you look at it with a transmission electron microscope called TEM, even though the particle size is large, such as 200 nanometers and 30 nanometers, the crystal size is much larger, but packed tightly. And this can be produced in large quantities. At present, almost all domestic manufacturers can produce this lambda titanium pentoxide. It didn't exist before, but now that it's been found, everyone can make it. What's interesting about this material is it's a black powder, and you cannot measure powder, so we applied pressure to make it into pellets. And under pressure, it changed from lambda crystalline structure over here to beta, which is well known, and we did this through pressure. We wondered what was happening, and we checked the pressure. And we found that the change from lambda to beta, this is the phase ratio it occurred at 60 megapascals, which is 600 atmospheric pressures. Now you may think 600 is large, but this is an oxide. It's a ceramic. And thinking about ceramics, thinking about 60 megapascals, the pressure of a stiletto heel is said to be 10 to 12 megapascals. So if you step down hard with a stiletto heel, that will cause the transition. This is an oxide material that undergoes a phase transition at the lowest possible pressure. And when it changes under pressure, the material radiates heat. From lambda we apply pressure, and at beta releases heat. That's the phenomenon we observed. The heat energy was 240 kilojoules per liter, As you can see below, the solid-liquid phase transition of water and ice is 320, and for ethylene glycol 165, for paraffin 140 kilojoules per liter. These are typical solid-liquid phase transitions, but this is a solid-solid phase transition, but it can release comparable heat energy. In addition, by applying pressure, we obtained beta Ti305. We raised the temperature, and at 190 degrees, it returned to lambda again, and was absorbing the same amount of heat energy. At 190 degrees from beta to lambda, the material stored great heat as it underwent phase transition. To repeat, this is the horizontal axis, XRD, but please just look at the peaks. The lambda decreases, pressure is applied, and the beta increases. And when the temperatures raise, the beta decreases and returns to lambda. Through pressure and heat, it will come and go between lambda and beta. That's the material we discovered. This is just a ceramic, just a titanium oxide. That's the important point. This is the result of combining experiments and theory. The beta Ti305, you warm it up to 190 degrees, it makes a phase transition to lambda, and it remains in the lambda state when it's cooled down. So, only when pressure is applied, it releases this much heat, the difference here. The conductivity is like this, like sensible heat storage materials in powder form, and when it cools down, it's like bricks and concrete, sensible heat storage materials. But even if the phase goes back, it keeps the latent heat, and the heat will only be expelled by pressure when it's pushed. And this is why the blue bricks can store heat energy for a long time. As I said at the beginning, this material solves the time gap issue and has been attracting attention. Let's take a look at the mechanism.
The mechanism of pressure-induced phase transition is explained using the thermodynamic model. Gibbs free energy versus lambda phase fraction curves are shown with lambda phase on the right and beta phase on the left. Lambda phase, shown with blue balls, is maintained at all temperatures due to the energy barrier between the two phases. Here, we focus on the Gibbs free energy curve at 300 Kelvin and take a look at the effect of external pressure. By the application of pressure, the Gibbs free energy curve gradually changes, and at 60 megapascal, the energy barrier disappears, causing the phase transition from lambda to beta phase, shown with the red ball. When the pressure is released, the energy barrier reappears, but beta phase is maintained since it is energetically stable. Next, the heat storage process and the pressure-induced energy release process is shown. When beta Ti305 is heated, it transforms to lambda Ti305, accumulating the latent heat energy, and the lambda phase is maintained in the cooling process due to the energy barrier in the Gibbs free energy curve. By applying pressure, the energy barrier disappears, and pressure-induced phase transition occurs from lambda to beta phase, releasing the accumulated heat energy.
Now, at this level of low pressure, the lambda and beta's thermal energy itself does not flip. The energy doesn't change that much. There's an energy barrier. There's this slight energy barrier which stops this. That's why pressure causes change. That's the mechanism. And this is not just by chance. From the beginning, we designed it this way. Otherwise, we wouldn't have found it. As I said earlier during our phase transition research, if we had something here we could catch and store, that was the idea. And we tried it with various materials, and this was the first material where it worked. In that respect, in heat storage, we have shown a new direction. As a new concept, heat storage ceramics is what we are proposing. Lambda with weak pressure becomes beta, and then beta goes back to lambda. Even long term, this new material can store heat energy. Where can this be used? This is joint research with Toyota Motor Corporation. The material is used with internal combustion engines, around the engine of an automobile, or around the exhaust gas, which improves the fuel efficiency. That's what the patent says. And there's great potential on the other hand. EVs are becoming popular, so gasoline engine cars will probably decrease. But still, that's the effect our material has. And the other thing is why we started this project in the first place. Over here, this is a solar thermal power plant in Europe, Spain, where there's extremely strong sunlight over a wide area. And over here, there are lots of mirrors with oil pipelines inside the mirrors, gathering the light from the mirrors, warming the oil inside the pipes. I hear the oil temperature rises to around 250 degrees Celsius, and they power the turbine. But what about at night? At night, we use the heat stored in the daytime. There's a heat storage tank used to heat the turbines. What's inside the heat storage tanks? Bricks. Our material already has the properties of bricks, so if we stored heat energy, latent energy, then release it, that might lead to effective usage. That's what started it all. This isn't a solar power generation system, it's a solar heat power generation system. It's very low tech, old tech, but on the other hand, it's also very versatile. And this is the actual heat generated. You can see how much heat is generated at the moment when pressure is applied. The heat is released immediately. And how much is released, we're using thermography to look at this. We placed material on an acrylic plate and tapped on it. And the moment we tapped on it, at 0.07 seconds or 70 milliseconds, we get to 126 degrees. From 28 degrees, it heated up by about 100 degrees. That's how the material releases heat. We worked with this company, Panasonic. Heat accumulation of 196 degrees Celsius can be brought to below 100 degrees Celsius. 67 degrees. Or when temperatures exceed 100 degrees, it can be used in a variety of places. Here we have a power station, and the power station throws away a lot of heat below 100 degrees, dumps it into seawater. This is a waste of heat energy and at the same time harms the environment, which is not desirable. So why don't we make effective use of it? That's one of our suggestions. Various applications are possible, and although we only touched on pressure, other than pressure, current-induced and optical switching are also possible, and this material also transforms with light. This is an example. When exposed to light, lambda changes to beta. The brown is beta and the blue is lambda. With a microscope, this is a view from above, and hitting it with a laser beam makes it transform, and it goes back and forth. A ceramic changing with light was not common knowledge before. So from the perspective of photo-induced phase transition, at room temperature, a ceramic changing in a reversible manner with light. This is the first time this has been observed. In the area of fundamental research, I mentioned earlier about the NIDO project. And in the area of basic research, we've also conducted special new research, and one of them is with France's CNRS, International Associated Laboratory. As I mentioned at the beginning, this year in Switzerland, the X-ray free electron laser facility, Swiss FEL, was launched. And as its very first project, they used our material, and their device observed photo-induced phase transition dynamics at high speed. And their observation showed that this actually happens. And what was interesting was, when exposed to light, there's phase transition, but normally at first we thought the light would hit and the heat would be released and spread, and then there would be phase transition, and that's what we all thought, originally, in the case of this solid. But when we tried it, the light hit the solid, and the speed of the flame spreading and the speed of the phase transition were pretty much the same, really fast. New phase transition essentials have been discovered, and there was a lot of interest. So deep basic research and applied research are both necessary. They both exist together. With this in mind, we're now communicating with people overseas. At the launch of the Swiss FEL, the director broke out the champagne to celebrate our data. That's what this photo is showing. It was a great honor, and I never thought it would make them so happy. The light is so strong, organic material would burn up and disappear, so we thought you have to use oxides like ours, and they used our material in this way, and the joint research went very well. Regarding lambda and epsilon, before publishing academic papers, we made patent submissions first. With companies, we have a lot of joint research. This shows you the patents. JP stands for Japan, US for the United States, CA for China, DEE for Germany, and so on. Both in Japan and overseas, I think you can see 68 here. There are actually more. There are 136, I think. For our new material, that have all been patented. What you're seeing here is only for epsilon and lambda, and the total number of patents has already reached 266, so about half have been patented. Starting from basic research, through such encounters will lead to applied research and innovation in science and technology. Materials that can be of use to the environment, contributing materials that can do that. As someone involved in manufacturing, that resonates most with my heart. As you can see in my summary slide, starting with fundamental research through awareness towards social contribution. That's what I wanted to talk about in my presentation. Thank you very much for your attention. That's all from me.